This video lesson corresponds with chapter 15 of your text, although it's not covered in a specific section, but we are going over titrations and we'll have an experiment this week on titration. So this video lesson specifically covers titration. You'll remember we finished last week with this important relationship in chemistry that the pH plus the pOH is equal to 14. This is derived from the fact that in any pure water sample, the molar concentration of H plus or OH minus ions are always 10 to the negative 7th. And if you take the negative log of 10 to the negative 7th, you get 7. So that's the pH, same with the OH minus, and taken in the inverse, the 10 to the negative pH is equal to the molar concentration of H plus. So these are important relationships, and we'll use these to solve problems like you solved this weekend for your homework. For example, what's the molar concentration of the hydrogen and hydroxide ion in a solution with a pH of 4.2? So we use this relationship, pH plus pOH equals 14, to solve these relationships. Let's do the hydrogen ion concentration first. So we know that the pH is equal to 4.2, so we use 10 to the negative pH to figure out the H plus concentration, and that is shown here. So the hydrogen ion concentration, substituting 4.2 in for the pH, the hydrogen ion concentration is 6.31 times 10 to the negative fifth. That's pretty straightforward. But we also need to figure out the the hydroxide ion concentration. And by subtracting 4.2, the pH, by subtracting 4.2, let's underline that, 4.2 from 14, you can figure out the pOH and then substitute in as follows. So the pOH is 9.8. OH minus concentration in moles per liter is 10 to the negative 9.8, and the hydroxide ion concentration in water is 1.58 times 10 to the negative 10th. Pretty straightforward. So this is all heading us toward a quick section on neutralization, where we will use titration to analyze the molar concentration of an unknown compared to a known. Remember, neutralization is an acid and a base reacting to form water and a salt. It's always ionic. And you remember from an ionic expression, you have a total ionic equation. The total ionic equation is shown here for the neutralization of sodium hydroxide and hydrochloric acid. Of course, you always produce water and a salt. Water is not ionic. Everything else is ionic and dissolved in aqueous solutions. We can, remember, cross out our spectator ions, things that show up on both sides of the reaction. Sodium is one, chloride is the other, and the net ionic equation then for the neutralization of any acid-base reaction is always the same. H plus and OH minus yields H2O. What's important from this, remember, is that the stoichiometric coefficient of H plus and OH minus are always the same. It's always 1 to 1. So moles of H plus equals moles of OH minus to get a full neutralization. And you use that in analyzing an unknown acid or unknown base compared to a known of the opposite species. So an acid-base titration is a titration in general is a really important technique in analytical chemistry, where you determine the concentration of an unknown solution by reacting it against a known or standard concentration. We are going to be doing an acid-base titration, but there are many, many different kinds of titrations in chemistry, including redox titrations and titrations of chlorides, all sorts of things when you react a known against an unknown. The technique is as follows. You just simply have to have a way of very precisely measuring volumes of both the known and the unknown. And in addition, usually an indicator of some sort is used. And remember, an indicator is something that in general changes color when specific conditions are reached. So how do we measure volumes very carefully? Remember, we use this piece of glassware shown on the right and in a diagram on the left. It's called a burette. And a burette, I think there's one there in the classroom that you can inspect. but a burette is calibrated to the tenths of a milliliter very carefully, and therefore we can estimate to the 100ths of a milliliter in between those calibration lines. Going back to this slide, a standard solution is usually your known, and the standard solution in most of for our purposes in honors chem is going to be something that's calibrated out to the 1,000th of a mole per liter. It's very carefully and accurately determined. So you measure an unknown against a standard solution, and by measuring the volume carefully, you'll know both the molarity and the volume, hence M times V, number of moles, for your standard that's used, and you can compare that with the volume of your unknown. So here's an example. Something that we might use as a standard is 1.039 molar sodium hydroxide, and you know you've not seen anything past the tenth of a molar in precision of determination, precision of concentration. You've not seen that yet. So a standard solution is something that's very carefully determined. So how do you go about doing a titration? Well, here are the steps. First, if you have, well, first, of course, for any chemical reaction, you write a balanced chemical equation for the reaction. That's the first step for anything, because you need to know any stoichiometric coefficients that might be important. Second, once you have completed the titration, you'll have the volume of the standard, or the known, which was added to the unknown. And if you know the volume and the molarity, you can do M times V equals number of moles. So you calculate the number of moles needed to neutralize the unknown, and then take a look back at the stoichiometric relationship from step one, the balanced chemical equation, and see if there is any stoichiometric conversion to do, any mole ratio conversion. And then you compute moles of the unknown that were neutralized, and then you calculate the molarity based on the two things that you know. You'll know the number of moles. Let me change my pen. You'll know the number of moles right here, because you calculated that in step 5, moles needed to titrate or neutralize the unknown. And you'll know the volume, which was very carefully measured at the beginning of the experiment. So you can calculate M, the molarity of the unknown, based on this relationship. The only thing to be careful of is if you use our shortcut from the previous chapter, if you use normality, which is perfectly acceptable, to remember that if you've calculated normality of the acid, if it's something diprotic like sulfuric acid, to convert back to molarity, because the normality will be twice the molarity for a diprotic acid. And that was a lot to absorb in one slide, so why don't we go through an example of a titration shown here. So let's say we have an NaOH, a sodium hydroxide standard of molarity 1.07 moles per liter, as shown here. And we have an unknown sulfuric acid solution. We carefully measure out 10 milliliters of that unknown, titrate it to neutrality, and it takes 19.7 milliliters of the sodium hydroxide standard to titrate that to neutrality. We're probably using phenolphthalein as an indicator, which you remember from last week turns bright pink. So first step, of course, is to write a balanced chemical equation. That's shown here. You guys have seen this before, so I'm going to move quickly through this. And second step, calculate the number of moles of standard of your known that you use to titrate to neutrality. So M times V is 1.097 moles per liter, shown here, times the volume, which we use 19.7 milliliters. Convert that to liters, don't forget, and you get the number of moles of sodium hydroxide used to titrate the unknown to neutrality. That's shown here. Okay, the next step is to do the conversion, the stoichiometric conversion from our balanced chemical equation. Now remember, we have a 2-to-1 relationship here. We figured out the number of moles of sodium hydroxide, and notice it's half the number of moles of sulfuric acid, 2-to-1. That mole ratio is shown right here, So we take the number of moles of sodium hydroxide that we know from the known, we divide it by 2, and we end up with the number of moles of sulfuric acid used to neutralize. And then, since we know the volume of the sulfuric acid that was given right up here, 10 milliliters of our unknown, we just do a quick molarity divided by, number of moles divided by volume to get molarity. So here's moles divided by volume, 10 milliliters, so we end up with a molarity, 1.081 moles per liter of sulfuric acid. Now, this slide, please don't copy. We're going to go over this again when I return to class, hopefully on Wednesday. But the steps in a titration are pretty quick when you actually do a physical titration. And I'm going to demo one in class on Wednesday, and then you guys are going to do one on Thursday or Friday of this week. So the steps of a titration are this. First, you measure a volume of unknown in the beaker, very carefully measured volume. In our previous example, we had 10 milliliters of the unknown sulfuric acid. And then you add some indicator and measure the pH and move on to your next step. You start adding, you have a full burette filled with your known concentration of your standard, sometimes called the titrant. And very slowly you start adding that to the unknown. If you have a pH meter in there, you can measure pH and collect pHs as you go. And you keep going until you reach what's called the equivalence point. And the equivalence point is the point at which you reach neutralization in an acid-base titration, where H plus equals OH minus. And you'll usually have a color change from your indicator at that point. And then you've reached the end of your titration. You can start doing your calculation. You record the volume of the standard added, and you march through the same sort of calculation shown here in the previous example. Now, right now, whoever's covering class is going to press pause and pass out this mini lab, which I'm going to demonstrate a titration on Wednesday. We're going to determine if a standard sample of commercially available vinegar from Giant or another supermarket is legal. By law, vinegar must be 5% by mass acetic acid. We're going to titrate some commercial vinegar against a known concentration of sodium hydroxide and see if we can determine if it is actually 5% by mass. Now, you can read the procedure and the problem statement. For homework tonight, though, you have the 2 pre-lab questions. The first one is, as you expect, write a balanced chemical equation for the neutralization between vinegar, and vinegar is acetic acid. The formula for it is shown here, right here, and it's that first H is the ionized species right there. So write a balanced chemical equation. The second one is a little more challenging, and it is calculating the molarity, not percent by mass, which is what vinegar and food products are measured. Concentration is measured in percent by mass here. We want to figure out the molarity of the acetic acid solution. So how do we do that? Well, I'm not going to tell you much more than this, and here's a hint. You must assume a certain volume of the vinegar first. Now remember, molarity is moles per liter, so figure out a good initial volume to assume and calculate the mass based on the density. And that's all the hints I'm going to give you. So good luck. You may start work with that. You can work with your partner, I think is fine. And you have this due for homework tomorrow. And in addition, no, that's probably good enough. And we'll do this for homework then. And I will hopefully see you on Wednesday.